Imagine a world where equations paint the canvas of reality, where the secrets of the universe are written in symbols, and where mathematics become a key to unlock the mysteries of our existence. Partial differential equations, the enigmatic equations with their distinctive curly D notation, are the hidden language of the universe. But what exactly are they, and why are they so essential? Why do we call them partial differential equations? Who discovered the curly D notation? Today we embark on a thrilling journey, a journey into the heart of one of the most powerful tools in the mathematical arsenal, partial differential equations, or PDEs. PDEs are the threads that weave together in the fabric of the cosmos, the language of change, the equations that govern everything from the motion of galaxies to the flow of blood in your veins. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this new video, Partial Differential Equations, and we would be solving puzzles of nature with PDEs. First, let us look into what is a partial differential equation, and I will give you a very simple English example. So the first definition tells a partial differential equation is an equation that involves an unknown function of two or more independent variables and its partial derivatives with respect to those variables. A partial derivative is a derivative taken with respect to only one of the independent variables while keeping the others fixed. Now you see, already I have underlined the most important and significant part of this definition of two or more independent variables. I will expand the same definition in the second part, which you see right on the screen now, and I have underlined another part which is called involves an unknown function of two or more independent variables. This is important, and its partial derivatives. And what is more important is the last line, that with respect to one and only while keeping the independent variables and other fixed. So if we take a very simple equation, for example x squared minus 3x plus 2, it is generally in algebra we take x is unknown and we solve it. Now the most striking feature is this one. The key defining property of a partial differential equation is that there is more than one independent variable, and this is something which we are going to see, and we are going to further look with simple examples which will make understanding of PDEs more simpler. Now at this part of our video, what we have seen is that we have seen it in plain simple English. But as we know that we are dealing with mathematics, so what about a very simple example which will elucidate further understanding of this concept of partial differential equation. So we see here y equal to x squared. So an equation with one independent variable is an equation in which the value of the dependent variable depends on the value of only one independent variable. You can see here x squared is the independent variable and y is the dependent variable. So in this equation, the value of the dependent variable y depends on the value of the independent variable x. So whatever the value we put in, we get the result. So here it is, the value of the dependent variable depends on the value of the independent variable. Let us see another example which is quite familiar. I think you can understand y equal to mx plus c. Here again the dependent variable is y and the independent variable is x, and m and c are basically constant. So equations with one independent variable can be linear or non-linear. Linear equations are equations in which dependent variable dependent variable is proportional to the independent variable. Now you can see in this equation y equal to mx, the value of the dependent variable is y, depends on the value obviously on the independent variable x, and there are two constant m and b. Now there can be more examples which are very simple, and let us see one by one. One is this one, y equal to x squared plus bx plus c. This is a quadratic equation. Then we get y equal to e to the power x, which is an exponential, and we get this one, y equal to log a plus x, which is a logarithmic equation, and y equal to sine of x, or y equal to cos of x, or y equal to tan of x. So it goes on and on. So these are simple examples of, I would say, dependent, independent variables and what we know in general. Now let us see a very simple example in which we can understand what we saw in plain English, that the equation of partial differential equations. Okay, so we see here that an equation with one independent variable is an equation in which the value of the dependent variable depends on the values of two or more dependent variables. So I am repeating the same definition, but I am giving two or more independent variables. Z equal to f of xy, dependent variable is z, and here I have underlined independent variables are x and y. So the value of the dependent variable is z depends on the value of the independent variables x and y. Similarly, u x of y equals to 0. So x and y, these are the u is the dependent variable, whereas independent variables are x and y. So here you see the dependent variable u is a function of two independent variables. What is that? X and y. This can be any function. It can be a heat function, wave function. We will see and explore later. So in this equation, the dependent variable u is a function of two independent variables x and y. This equation states that the value of u is equal to 0 at every point in the domain of x and y. Don't worry if you don't know what it is about domain, we will deal it later. That is quite simple. So this is what is called a partial differential equation. That means more than x, y, z, t and so on. So this is what is called partial differential equation, and this is a kind of a summary, a simple understanding. A differential equation is called ordinary if the function depends on one single variable, and partial if it depends on more than one variable. Now you see that we have till now we have understood that equations dependent, independent. So if within the function there are more than one variables, then we call them at partial differential equations. But these are given in terms of functions. But the question is that how does the partial equation actually look like? Let us look in the next part of our video. So here before we end, y equal to f of x and y equal to f of x, y, z, t and so on, just to make you understand. So let us now see that how actually the partial differential equation looks like. So here is here are a few examples. So here you can see del u by del t equal to alpha nabla square u. This is the famous heat equation. Then del square u by del t square c square nabla square u. This is the wave equation, and this is just any other equation. So this is how it looks like. So you can now understand that if you see something with this curly d, then you can understand, okay, this is not an ODE but a partial differential equation. We are also going to explore a fascinating history, who and how this del curly d was invented. I will show in this next part of our video. But before that, we need to take this example, and you can see this one, t, x and y. These are involving functions of three variables. So now you can see how it looks like, and these are more than one variables, and this actually involves the function. So we will take forward this equation del u by del t equal to alpha nabla square u. Don't worry about these signs etc. You can just consider them to be simple variables, and I will make you understand about the core factor, the basic root, and then you can understand on your own. Okay, so the first part, del u by del t. This term actually represents the partial derivative of the function u with respect to time t. So this term is actually the rate of change of temperature, which is the dependent variable, with respect to time, which is independent variable, and it tells that how the temperature of a room or a specific coffee cup, how it changes. This alpha is basically a constant. This u is basically the dependent variable, and that is what I was telling you. The temperature u is a function of both space and time, meaning it can vary from different position at different time. Obviously, the temperature of a specific room or a coffee cup of any kind will actually will change from one place to another. That is from space to time. So x and t, you can say these are actually changing from space to time. Now you see that ux of t, this is actually representing the temperature at specific point x at a specific point t. So del u by del t is basically the rate of change on the dependent variable with respect to the independent variables, and the temperature u is basically the function of space and time. Now what are the dependent and independent variables? Again, a quick recap. Independent variables are space, basically are space x and time, which actually is time t, which presents, and this nabla square is basically the Laplacian, which is a second order partial derivative and can also be written as this. So the independent variables are basically space and time. I mean to say the space which represents along the one dimensional, maybe the x-axis, and the vertical one, time, representing the time axis, so it continuously changes. And this change is being actually denoted by this curly d, that is the I would say the partial derivative, which actually represent the change of temperature. So independent variables are t and x, dependent variable is u, Partial derivatives are del u by del t, or as I told you, del squared u by del x square, and the Laplacian operator is the Nabla square. So this actually gives us a kind of a fair bit of idea of what we are leading into. I mean to say dependent, independent, how it looks like and how we write. Now there is a very, I would say, pertinent question. Now why we call it as partial? Why don't we call it as full derivative or a complete differential equation? Why it is called partial? Coming up in the next part of our video. Okay, before we go ahead, so here's a quick summary. The heat equation is partial differential equation because it involves partial derivatives of dependent variable to more than one independent variables, which is del u by del t, and the second partial derivative with respect to space is del square u by del x square, which is also written as a Laplacian. Now what I was telling you is that why do we call it as partial? Coming up in the next part of our video. Here I will try to make you understand why it is called partial and not full and complete. Now you see, partial differential equations are called partial because they involve partial derivatives. So let us break down what we are trying to see. So partial differential equations consist of two words, that is partial derivative. Now what do we mean by derivative? So we already know that a derivative measures how a function changes as its variable changes. For example, the derivative of a function of f of x with respect to x can be denoted as df by dx or f prime with the prime notation, and it tells you how the function's value changes as the independent variable x changes. This is very simple, and we have all learned in our high school this is called a derivative. Now when we talk of, so it shows you how the value changes, independent variable x changes. Now when we talk of partial derivative, you see already there are two variables x and y. So when you have a function of multiple variables such as f of x and y, you can take a derivative with respect to one variable while treating the other variables as constant. Remember, you are taking a derivative with respect to one variable with taking the other variables constant. So the partials of del f by del x actually I would say measures how the function xy changes concerning the variable x while keeping y constant. Similarly, del f by del y measures the change concerning y while keeping x constant. So first let us look into this. Del f by del x tells the partial derivative del f, that is how the function f of xy changes concerning the variable y keeping x constant. Now if I say del f by del y, which I was just telling to you that del f by del y measures the change. It actually measures the change concerning while keeping concerning while we keep the x constant. So at one place we are keeping y constant, we are keeping x constant. Now these are called partial derivatives because they capture the function changes partially, not completely, with specific variables. So here is a quick summary. Del f by del x y while keeping x constant, and del f by del x is x while keeping y constant. So this is how we do. So now when we summarize all the words partial and differential and equation, we get this. PDEs are called partial because they deal with partial derivatives, which capture how a function changes concerning individual variables while holding the other variables constant. The terminology helps actually to distinguish from ordinary differential, which involve derivatives with respect to one independent variable. Now you see why it is called partial, because we are not totally differentiating it. We are differentiating one partially while keeping the other constant, and when we are differentiating the y, we are keeping the x constant. That is why it is called partial, not complete, because we are not completely, I would say, differentiated. We are differentiating it partially. Now automatically from here there might be a question in your mind that what is the difference between partial differential equation and ordinary differential equation? I would use the acronym PDEs and ODEs. Let us look in the next part of our video that, okay, so this is a summary. Again, a partial differential equation is an equation that involves partial derivatives, and in other words, it shows how the rate of change of a function depends on multiple independent variables, and that is why it is partial. So what is the difference between partial and ordinary differential equation? I will take a very simple example while explaining this. So what I will do is that I will consider simple ODE, or ordinary differential equation, which describes the population growth of maybe a population or a single species or something. So here you see in this equation, dn by dt actually represents the rate of change of the population with respect to time. The R denotes constant, representing the growth of rate of population, and this capital N actually represents what we call is the population's size. That means it is basically a function of time. So this is actually what is called an ordinary differential equation. Now let us consider a simple partial differential equation that describes the heat along a one-dimensional rod over time. So here you see this one, del squared U, I would say by del x squared. This represents the second partial, second partial derivative of temperature with respect to position. This del u by del t represents the rate of change of temperature with respect to time, and alpha, as we know, is basically the constant. So this actually represents the temperature, which is a function of both time t and the position of the rod, that is x. So these two equations right at this moment, which is showing on the screen, is a clear distinction between ODEs and PDEs. One variables, but here there are two variables, both time and t. Both time and the position, that is x. Now it is a quick time that we should get a key difference in simple English to understand the key differences between ODEs and PDEs. Number one, obviously it is independent variables, because ODEs involve a single independent variable, typically time. PDEs includes multiple independent variables such as time on one or more spatial dimension. It can be x, y, z, etc. and so on. In the heat equation, as we see, it is U, depends on both t and x. Now, in terms of dependent variables, ODEs handle only one dependent variable that depends only on one single independent variable. In PDEs, there can be multiple independent variables. For example, the temperature U in the heat equation. Another key difference is the spatial variation. What I mean to say is that ODEs describe typically with change with respect to a single variable. I mean to say often time without considering the spatial variation. And PDEs are described to describe both vary both in terms of time and space. So they actually account for spatial ingredients, and it actually accounts for the temporal changes. So what we can tell it in summary is this one, that the primary difference between ODEs and PDEs lies in the number of independent variables and obviously the spatial variation. So ODEs involve a single independent variable and describing changes over time, while PDEs involve multiple independent variables including spatial dimensions and describing changes over both space and time. Now, as I was telling you that partial differentials are partials because we are not totally differentiating it. We are differentiating one, keeping other constant, and then when we were doing the second, we are keeping the first constant. So this brings up to our next very important, I would say, concept and understanding. What is a partial derivative and what is a total derivative? This is a very key understanding. Now you see, in partial derivative or total derivative, both of this accounts for a function changes, how a function changes with respect to variables, obviously. Now partial derivative actually changes the rate of function with respect to one's variable, as I told, while keeping the other constant, and total derivative tells it take into account the simultaneous changes in all variables. That means it will take into account all the different variables. Now in order to talk more on this, you can look into this video of mine, partial derivative versus total derivative, which is a complete totally dedicated video where I have talked about the difference, taking examples and explaining things in a much more simple fashion, as this video is basically on partial derivative, so I won't be explaining in total. You can just go to my playlist, in the videos in the Physics for Students, and you can find out a nice video which speaks only on this concept, what is the difference between partial derivative and total derivative. Now, right now what you see is that these are symbols. You can see total derivative as the simple Latin or the English word d, whereas partial derivative is a curly d. The question is that, is this a Greek letter? Is this an English letter? Is this a Latin letter? It is a Roman letter? What it is? this is the time that we should embark on a wonderful history to discover that how this sign actually came into being and who discovered that. So now we will look into the sign del that we use and how it was discovered in the next part of our video. Now first is that you know that this is delta. This is a Greek alphabet. This one is also a Greek alphabet, but this is actually not a Greek alphabet. And this is what is D, which we already know D as a Latin alphabet. Now what do I mean by not a Greek alphabet? Let me explain in the next part of the video. So you see here that I have already made a video which is quite popular on my channel, which is delta, d, del and all partial derivatives. So you can go to my Physics for Students channel and you can find out the concept building, the difference between these four signs in details. As you can see, it is more than 34 minutes, so you can find it out what is actually going on. But here comes the basic idea of the using the sign D. This one is actually called the Cyrillic alphabet. This is how the original Cyrillic alphabet looks like, and in phonetics it is used as D indoor. That is why you see dx, dy or something like that. In italics it looks like this, and in Cyrillic numerals it has a value of 4. That means in the numerals in Cyrillic alphabet it is 4. And this was first used by this person in 1770 by Nicolas de Condorcet. And we are now going to look into the original foundation of how Nicolas de Condorcet and other mathematicians discovered the usage of this partial differential equation. Here is a quick summary. Delta, it is for finite perceptible change to find the difference. This one is approximate, not exact function. D is the infinitesimal imperceptible change, and the curly D is infinitesimal change, and it is used in to partially differentiate. A kind of a quick chart which would give you an idea. Okay, so we understood that this is obviously not a Greek letter. It is used for partial differential equation and is used as a Cyrillic alphabet. Now you see the first usage of this curly D was done by Marie Jean Antoine Nicolas de Caritet, or known as Marquis de Condorcet. He was a French philosopher and mathematician. His ideas included support for a liberal economy. Now in 1770, Nicolas de Caritet actually used this in his French work. I have translated it. Maybe the translation is not good. It means memory on partial difference equations. And the original French is this. I would also try to make a note to our viewers who are watching this video that this might not be the exact French translation, because I have used Google Translate, which might be sometimes a bit different. So throughout the rest of this memoir, dz and del z will designate either two partial differences of z, one of which with respect to x, the other with respect to y. So you see that immediately we can see that what it is all about. And the Marcel de Condorcet actually uses this French, and when we translate it in English language, it actually comes to this. So this was, I mean to say, historically in 1770, the first usage of the curly D, which was the sign that is used in partial differential equations. Now this curly D was first used again in the form of del u by del x by this person, Andrea Marie Legendre. Now Legendre actually used this in his this kind of a work, which is again translated Memorandum on how to distinguish maxima from minima in the calculus of variations. And the curly D was first used by Andrea Marie Legendre in this form, curly D in the form of del u by del x. And this is actually the original, I think it is German, which is written, and this is actually the English is given. Again, I make a note that this translation might not be exactly correct, but this is just to give you an idea. To avoid ambiguity, I represent del u by del x, the coefficient of x, in the difference of u, and by this the full difference of u divided by dx. So Legendre's usage is another usage which you can see of the curly D, and this is the book, and this is the exact German line which tells the difference and the usage of curly D. Now this gentleman Karlov Gustav Jakob Jacobi, actually Legendre abandoned the symbol which was reintroduced by Karlov Gustav Jakob Jacobi, and in this book, which translates again from German to be on functional determinants, and this is again, I would say the translation might not be correct because I'm using Google Translate, which is not always right. So since the accumulation of hooks tends to be more troublesome both to the reader and to the writer, I prefer the characteristic D, vulgar differentials, and to denote the characteristics of partial differentials. So this actually shows different usage. Legendre, Jacob Jacobi, and the other mathematicians, which actually gives you a kind of a root understanding of partial differential equations. This is not a kind of a Latin or Greek. It is a Cyrillic alphabet, and it was first used by Anton Nicolaus Caritat, then it was used by Legendre, and then it was further used by Karlov Gustav Jacobi. Now, this partial differential equation is used extensively, obviously, in mathematics, but in one very prominent and I would say important equation which guides the laws of nature. What is that? Let us find in the next part of our video. So how partial differential equations are used in Einstein field equations. Don't worry, I won't go deep in understanding partial Einstein field equations, but here is a quick understanding. This is the partial differential equations of Einstein's field equation, and as you can see, R mu nu actually denotes the 4 dimensions of space-time. G mu nu also denotes 4 dimension of space-time. Here also again it is 4 dimension of space-time, and this one also is 4 dimensions of space-time. So if you add it together, what you are looking at Einstein field equation is actually a collection of 16 partial nonlinear differential equations which has been put into one single equation, and this mu nu actually are the indices of space and time. So what you're looking is actually 16 partial differential equations. You can look further into my video of this, which actually explains a lot about Einstein's field equation for a beginner's complete guide, where I have dealt a lot about Einstein's field equation. This is just to tell you that how PDEs are important and how 16 partial differential equations are summarized into one Einstein field equation. But remember, these are equations because there are 16 partial differential equations involved in it. What you are seeing is just one. Now, having understood with all those, there might be a question in your mind that what kind of mathematics, what kind of mathematical understanding do I need to have in order to understand partial differential equations, or rather, how would I go in order to understand partial differential equations? Coming up in the next part of our video. So, as far as the mathematics is concerned, I would say definitely, yes, you need to have an understanding of calculus, because single variable and multivariable calculus is a fundamental, otherwise you won't be able to get the concept like derivative integrals, etc. Ordinary differential equations, yes, a strong understanding of ordinary differential equations is important because these are the building block of PDEs. I would also suggest to look into linear algebra, because you will see that when the matrix, etc. are coming, vector spaces, eigenvalues, matrices, partial differential equations, when they're mixed with the notations of linear algebra, becomes very cumbersome to look upon. So I would always request you to look into linear algebra, ordinary differential equations before going into partial differential equations. Also equations with boundary value problems, which sometimes comes as a problem for most of the student, I would request you to go first with lot of problems and understand what is boundary value problem, because to understand these would include the solving of PDE. Other than that, you can see mathematical analysis, complex analysis, physics and engineering, programming and numerical methods. Well, these are, I would say, these are not mandatory, but you can have options if you're going into physics or mathematics or engineering or complex analysis. Then before going into PDEs, you can learn also those things. Having said together, what again crops up might be in your mind that are partial differential equations difficult to learn? Are they very complex? Let us look why they are difficult, and once we understand the reason, then we can understand and find out the solution. So that is why learning the reason of its mathematical or is it complex or not, that is important. Coming up in the next part of the video, are partial differential equations difficult to learn? The answer is straight away no. Absolutely, PDEs are not difficult to learn, but it comes as a difficulty. Why? Because of these reasons. Point number one is that it includes a lot of mathematical complexities. Now, PDEs actually make more things complex than ordinary differential equations. These derivatives introduce multiple variables which sometimes become very confusing. Also, the second reason is that it includes multi-dimensional space, because they deal with functions or multiple independent variables, which introduces concept of working with multi-dimensional space. So obviously, visualizing and understanding solutions in higher dimensions can always be a big challenge. Boundary value, as I just told you, that solving PDEs typically requires the specific specification of boundary conditions and the initial condition, which can be a kind of a non-intuitive understanding and requires a deep understanding of the physical phenomena which is being modeled. We also find that there are diverse applications. PDEs are used to model a range of physical phenomena such as heat, conduction, to fluid dynamics, quantum mechanics, and understanding these intricacies might sometimes come as a daunting task. Non-linearity, because many real-world PDEs are non-linear. Why? Because they meant to be in terms of equation which are not simply proportional. For example, y is to x, but depend on a lot of variables. So non-linearity introduces additional complexities solving those equations. Classification of types, as I will cover in the next part of the video, that PDEs come in different forms: elliptic, parabolic, hyperbolic equations, which have their own distinct characteristics and solution techniques. So knowing them can again be something confusing. And lastly, as you know, graphically representing partial differential equations, that is physical interpretation, is not always that easy. So understanding the physical interpretation of the mathematical solution is very crucial. Interpreting them, showing them in graphs, well, it actually creates a problem, and these models requires a deep grasp of both mathematics and physics. So it is not at all difficult, but why it is difficult, now that we have understood this 1, 2, 3, 4, 5, 6 and 7 reasons, you can very well understand that these are the reasons, and if you overcome and understand those, then partial differential equations are super easy to understand. So that brings up, okay, so why PDEs are important in physics and mathematics? Just a quick overview. First is that the modeling of physical phenomena, yes, it is important because PDEs are fundamental tool in describing the behavior of physical system, and starting from heat conduction, fluid flow, electromagnetism, whatnot. Thirdly, yes, it is universally applicable. So a broad range of spectrum problems, starting from, genetic engineering to anything, is being covered by PDEs. So it is super important that we learn them properly. Quantitative predictions, yes, scientists and engineers take quantitative predictions about the behavior of physical phenomena, and obviously the fundamental laws of physics like Maxwell's equation, Schrodinger's equation, Navier-Stokes equations and whatnot, the list will be endless. The fundamental laws of physics are being explained by partial differential equations. As you understand, nature is always at unrest. Nature is not always that whatever will vary here will be obeyed over there. Nature is very complex, and that is why we need multiple variables, and that is why partial differential equations becomes a very important tool. Okay, so here is a quick summary of what we have understood till now. So what we have understood is what is partial differential equation, how does the equation look like. We have also understood why it is called partial, the difference between PDE and ODE, what is partial and total derivative, link to the next video, you can look into it. We have seen how partial differential equations feature in Einstein field equation. What is the origin? Who are the mathematical discoverers who use the curly D sign, which is not a Greek or a Latin, it is a Cyrillic alphabet. And at all partial differential equations are difficult to learn. We have faced with the challenges and importance of partial differential equation, why it is so important, and we need to understand all of them. That's all for today's video. I really thank you for taking your time for watching it. If you have liked the video, hit on the subscribe button to get all the notification from Physics for Students. You can always contact me here in my email ID. This is my other channel where I am taking a little bit of more time to put up videos on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. That is all for today's video. I would wait for your comment. How do you like the entire idea of partial differential equations, why it is called partial, the origin, and a lot of fascinating histories. Physics for Students will continue surprising you with more such videos, but till then, goodbye.